In this video, we're going to have a quick look at the binomial distribution, which is a type of discrete random variable distribution, as we've looked at in the previous lesson. Goals for the end of this video is to know what is the binomial distribution, how would we recognize a situation that would enable us to use the binomial distribution, and we'll have a look at how you use the formula, what the formula is and where it comes from, and have a go at doing a few calculations by hand. And then there's a second video that will show you how the GDC can actually do all the calculations for the binomial distribution for you. And generally in the exams, you're actually able to just do it that way and type the values into your GDC. So as it says here, the binomial distribution, type of discrete random variable distribution, and it's about success and failure. The times when we're going to use the binomial distribution is when there's a fixed number of trials. So we're doing something a specific number of times. So it can't be something where we could be doing it indefinitely. It's got to be that we do it 10 times or 20 times or 100 times. And there's got to be only two possible outcomes. That's what the success and failure bit was talking about. So either something we're looking out for happens, which would be a success, or it doesn't happen, which would be a failure. So it's the one or the other. So for example, the number of times someone answers true to a question, or the number of times I get a heads when I flip a coin 20 times, or the number of girls in a certain class, or the number of times I get a 6 as opposed to not a 6. It's important that each trial is independent. So obviously the scenario needs to be that if something has been a success on the first trial, then that doesn't impact on the likelihood of it happening again on the second trial. And there's an important bit of notation that we use to show a binomial distribution, as at the bottom here. Often we'll use a capital letter X to denote the discrete random variable, just like we did on the previous video. But then this symbol here means that X is distributed by, and then the B stands for binomial. So we're basically saying, right, this is a binomial distribution as opposed to a Poisson distribution or a normal distribution or the other types of distribution we have. And we then give the key bits of information that you need for a binomial distribution, which is the number of trials and the probability of success, the probability of having a success on one of those trials. So these three examples here are all ones where the binomial distribution would be applicable. So X is the number of heads when a coin is tossed 20 times. So there's a finite number of trials, n is 20. There are two possible outcomes. I can get a head or I can not get a head, i.e. I can get a tail. And they're all independent. If I get a head on the first toss of the coin, it's no more or less likely that I'm going to head on the second. On the second one there, the X is the number of sixes when a die is thrown 10 times. So again, 10 trials. Getting a 6 one time doesn't affect the likelihood of getting a 6 the next time. And I can say I am either getting a 6 or I'm not getting a 6. Success or failure. And then finally, the test with a pass rate of 60%. X is the number of students who fail a test out of a class of 30. So I've got a fixed number of trials. I'm looking at the scores for 30 students. So N would be 30. And then I'm trying to look for the number of failing students, which is going to be a probability of 0.4. If 60% pass, then 40% must fail. So I've got a fixed probability of 0.4. Have a go now at what you think the distributions would be for these two examples. So let's have a look now at how we can actually then work out a probability by using these distributions. So we're going to try and work out what is the probability of getting exactly 2 6s when I roll a dice 4 times. So I've got 4 trials, n will be 4, and the probability of success, a success being getting a 6, is 1 in 6. So let's have a look at the ways that this could happen. I could get a 6 on the first roll, a 6 on the second roll, but because I'm getting exactly 2 6s, that would mean that I don't get a 6 on the other 2 rolls. And then those 6s can be interspersed a variety of different ways. In this case, 6 different ways. So hopefully you're thinking about how could you work out the number of ways these 6s could be arranged, because that's critical to this problem. And it's actually a combinations problem. We're trying to work out the number of ways of fitting 2 objects, these 2 6s, into 4 spaces. The order doesn't matter to us, so it's not permutations, it's a combinations question, and 4C2 would calculate the number of those combinations, i.e. 6 in this case. For each one of those combinations, the probability of getting 2 6s is going to be 0.0193. How do I calculate that? Well, there's a 1 in 6 chance of getting this, times 1 in 6, times 5 in 6, times 5 in 6. So that's going to happen on each one of those. It's the same multiplications that are being done, just in different orders, and it's happening on 6 occasions. So to then summarize that formula and that calculation, the probability that x is 2, if x is the number of 6s I get, what's the probability that the number of 6s is equal to 2? So it's equal to the number of combinations, 6, times, and then we wanted to see 2 successes. So we wanted to get 2 6s, and we therefore knew that we had to get 2 non-6s, i.e. 2 times when it was a 1, 2, 3, 4, or 5. And then if you calculate that, you get 0.116 to 3 significant figures. So this is the binomial formula. If x is distributed with the binomial binomial distribution, n trials, p being the probability of success, the probability of x being equal to a value r, so the probability of having, let's say, 2 successes or 3 successes or 4 successes, is NCR, so the number of combinations of fitting r objects into n spaces, and we would then want to have r successes, so we want the success to happen r times, so p to the power r, and then we would want to have n minus r failures. So we would want to see this not happening, i.e. 1 minus p, on the remaining occasions. So for example, if n was 10 and I wanted to have 2 successes, then this number over here would be 8, because I would need to have 8 failures if I'm doing this thing 10 times. Let's look at an example. Eggs are packed in boxes of 12. The probability that each egg is broken is 0.35, which is pretty high. Find the probability in a random box of eggs that there are 4 broken eggs. So the distribution we're looking at here is that we have 12 trials, and the probability of success, we're actually talking about a broken egg being a success, is 0.35. So what's it going to be? Well, this 12C4 is the number of ways the 4 broken eggs could be arranged within the 12 eggs I have in total. And then I want to see 4 broken eggs, so 0.35 to the power of 4, and therefore I want to have 8 unbroken eggs. So an unbroken egg is 1 minus 0.35, i.e. 0.65, and I want to have 8 of those, which then comes out, if you do the calculation, as 0.237. Let's look at another example. Eggs are packed, same example, eggs are packed in the boxes of 12. What's the probability that there are less than 3 broken eggs? Now this is where the GDC comes in really useful, because this is going to require quite a few calculations, which by hand is a bit of a pain, but the GDC will do it all in one go and just churn out the final answer. So let's have a look at how this would work. Less than 3 broken eggs. So less than 3 broken eggs means basically 0, 1, or 2 broken eggs. So we could say probability that x is less than 3, which is the same as the probability that x is less than or equal to 2, because this is a discrete distribution. And we could, if we're doing this by hand, we could calculate that as being the probability x is 0, add 1, add 2, i.e. the probability of having 0, 1, or 2 broken eggs. So we do each individual calculation. We've got 12C0, we want to have no broken eggs, 12 unbroken eggs, 12C1, 1 broken egg, 11 unbroken eggs, 12C2, 2 broken eggs, 10 unbroken eggs. Do all the calculation and you get 0.151. And you can see how really you couldn't get given these questions in a non-calculator environment, because you're just not going to be expected to do that kind of a calculation without the use of a GDC.